We're going to look at Chapter 8 today. The third exam is just on Chapter 7 and Chapter 8. Last week we looked at pure substances, gases, liquids, and solids. Now we're going to put them together. How do we deal with mixtures? In this case, homogeneous mixtures, solutions. All right. A homogeneous mixture can be two or more pure substances mixed together, and they're uniform throughout. In other words, any place you sample them, take a subsample of any solution, the composition of the pure substances will be exactly the same. They'll have the same percentage amount of every component. And we normally think of solutions as some solid dissolved in a liquid, like sugar in water or salt in water. But homogeneous mixtures or solutions can be anything. Any phases can mix together and make a solution. Liquids and liquids, of course, you can make booze, ethanol and water and some other stuff. Gases and liquids, you can make soda pop. Carbon dioxide is the fizzy part. We're breathing a mixture, a homogeneous mixture. We're breathing a solution, primarily oxygen and nitrogen with some other minor components. You can even make solid solutions. Brass is a good example, where you mix copper and nickel primarily. You can't do it while they're solids, of course, they won't mix. But if you heat them up, make them liquids, and then mix them together, you can make what's called an alloy. And that's a solid-solid solution once they have solidified, cooled down. Now, terminology. When we define a solution, the major component is the solvent, and there can only be one major component. Everything else is solutes, and you can have any number. Any number of solutes, but only one solvent. In most cases, the solvent is going to remain the major component no matter how much of the solutes you put in it, because you'll reach a limit where you can't put any more in. And that's usually at some point less than the amount of solvent. But there are some exceptions. Sucrose in water, table sugar in water will mix. You keep adding sugar. Eventually, you'll have more sugar in there than you did water to begin with. But since we started off with mostly water, with water as the major, we keep water as the solvent. If you make hummingbird juice, 50-50 mix, you can go higher than that. In fact, industries that use sucrose in their manufacturing very often transport the sugar they need in solution because it's easier to move around, as long as the process doesn't mind if you have a little water with it. I got a book on my shelf called "This is Liquid Sugar," and it's just all about how you deal with these concentrated sugar solutions. All right. This is just an example. That's probably, I would bet that that's probably potassium dichromate, because it's readily soluble in water, and it gives you that color. All right, I already mentioned two or more components, and one of them has to be the solvent. Another characteristic of solutions is that they have a variable composition. In other words, you can have a little bit of solvent or you can have a whole lot of solvent by comparison. And they can be separated by physical means. It just depends on what type of solution it is as to how you would separate them. If you have a, say, a solid like salt in water, you would separate them. And we did one of those, didn't we? Yeah. You just boil off the water and you got the salt left. That's a physical process. But there are other examples. And the properties of the solution change. With this variable composition, the properties change. For instance, there's all firemen take a course to be certified. Anybody, we got any volunteer firemen in here? No, okay. I didn't want to tell you something you didn't already know. They learn about flashpoints. In other words, you have a certain amount of fuel that can be dispersed in air. And below that amount, it won't ignite. And above that amount, it won't ignite either. So there's a range in there where the mixture, the solution, is dangerous. Another property, say you have, if you've made sugar water before, you know that it starts out just with the water is fairly, it flows easily. But as you add more and more sugar, it gets thicker. That's a physical property that changes with concentration. These solutes can either be molecular, or when they go into solution, they can break apart into ions. It just depends on what type of compound it is. If it is a compound, right? If it's not a compound, it's like carbon dioxide, well, that's a compound. Oxygen. You can dissolve oxygen in air more than you have now. And that's what we do in hospitals, like we supplement the oxygen. But it's still molecular. It goes into solution. Sugar, sucrose is that way, right? The sucrose molecule does not change when it goes into solution. It just associates itself with the solvent in various ways. And hopefully I get to talk about that a little bit. Sodium chloride, for instance, is an ionic solid. Any ionic solid that's soluble in water will break apart into ions. So in solution, you'll have sodium ions in aqueous solution and chloride ions in aqueous solution. These solutes, of course, will not settle out over time. You leave them as long as you want. As long as you don't let the solvent evaporate, then those solutes will not precipitate. They will not fall out of solution. And I mentioned this already. You can separate the solutes from the solvents in each other by physical means. So if we have a homogeneous mixture of 80 milliliters of water and 20 milliliters of alcohol, which one's the solvent and which one's the solute? Well, the major component is water, right? So water is the solvent, the alcohol is the solute. We have another term associated with this variable composition, and it's called solubility. There are many substances, particularly the ionic ones, that have a limit to how much you can put, what percentage composition you can make out of that solute in particularly water. We're going to be focusing on water. So their solubility is given in terms of how much will go into solution. And if you look it up in a reference manual, usually it'll say something like so many grams of your solute will dissolve in 100 milliliters or grams of water. If water is considered the solvent in that table. This is per 100 milliliters of water. This is not the volume after you add the solute. This is the volume of water before you add the solute. When you add them together, there's no guarantee that you'll have 100 milliliters of solution. It could be more, it could be less. And we'll talk about that in a minute also. And the conditions will be specified. Usually they either specify 0 degrees C, 20 degrees C, and sometimes 100 degrees C, right at the boiling point. In most cases, solids become more soluble in water with increasing temperature. There are some exceptions that go the other way. They become less soluble as you increase the temperature. And there's no theory that explains why that happens. There are some ideas. But for our purposes, it's just empirically determined. On the other side, if you try to dissolve a gas in water, as you increase the temperature, the gas always becomes less soluble. So solids generally increase solubility with temperature and gases decrease solubility with temperature. So if you put water on your stove, just take it out of the tap and put it on the stove and start heating it up. As it gets hotter and hotter, what do you see? You see little gas bubbles, right? That's not water. That's not boiling water. That's dissolved gas coming out of solution. And then shortly after that, the water starts to boil. So if you want to degas water, just heat it up till right below the boiling point if you want, or you can boil it. And then put it in a stoppered container to where no gas can get to it, and you've got degassed water for as long as your container is impermeable to gases. Okay. So here's an example of solubility of some ionic compounds in water at different temperatures. Lead-2 bromide increases solubility with temperature. Silver sulfate also. Copper-2 sulfate increases solubility. Sodium chloride. And notice, even at these given temperatures, the different compounds have different solubilities. It's characteristic of the solute and the solvent. Sodium chloride becomes more soluble, not a whole lot more, but some. Silver nitrate becomes more soluble. Cesium chloride becomes more soluble. There are a couple of examples I think I've got them flying in here. Yeah. Calcium acetate becomes less soluble. In fact, that's characteristic of some of the acetates. What's an acetate? Remember the polyatomic ions? Acetate is CH203 O2 minus. That's the acetate ion. Put a hydrogen on the front of it, you have acetic acid. Well, if you put it in solution, of course, you have acetic acid. So this acetate is the ion that the anion with calcium is our example. So we need two of them. So that compound is less soluble as the temperature increases. Ammonium acetate also does that. Seems like the acetates are a class of compounds that flip the solubility rule. So what's the effect of pressure on solubility? Let's see, let me make some more room. That's that. The effect of pressure on solubility is only measurable for gases. Gas solutes become more soluble with pressure. Liquids, solids, they don't care. You can run the pressure up to monstrously high values and it won't affect their solubility at all. But like I said, gases, pressure has a major effect on gas solubility. And as you increase the pressure of the gas in the headspace above the solvent, the liquid, particularly water, the gas becomes more soluble. And there's the law that governs it. Right? We talked about gas laws already, haven't we? Yeah, we did that last week. Okay, this is another law, but and remember, laws just say what happens. The concentration of the solution, concentration of the gas in the solution is equal to some constant, Henry's constant times pressure. Okay? So if you don't know the constant, then you can't use this formula for whatever you're studying. But if we use that model from our gas laws and do a before and after situation, then if we solve this for the constant equals concentration over pressure, and then this is one situation, and if the conditions change, right, that's equal to a constant. Now we have a before and after. That one is equal to this one. Okay. So if you know the before conditions and one of the after conditions, you can determine the other one, solve for the other one. All right. When solubility has been reached, the maximum amount of substance that can be dissolved at a given temperature, we say the solution is saturated. It won't accept any more solute. There are cases, quite a few cases actually, where under the right conditions, you can have more solute in that solution than you expect to have at saturated conditions. That's called supersaturated. Typically how you do that is you find out how much will dissolve in your solvent, and you put that much plus a little more. Choose whatever you want. But be careful when you choose, because you heat it up and you get all of it in solution for those solids that are soluble at higher temperatures. And then you set it on the desk and you let it cool with it undisturbed. And as it cools, it retains all of that dissolved solute in solution. Now, all you need is a disturbance, right? Shake it, stir it. Sometimes we used to reach in with our spatulas and just scratch the inside of the glass, and that would be enough to trigger the precipitation. The reason I said be careful about how much extra you put in there, because if you have crystals left over of the solute, then they will serve as a nucleation site, and you won't get your supersaturated condition. So it's a tricky situation. Unsaturated solutions are anything below the saturation level. It's just that simple. These other terms are qualitative, concentrated solutions. We have a large amount of solute relative to its solubility, but we're not at the saturation point. Dilute solutions are very small amounts of the solute relative to their solubilities. So these terms will vary depending on what the solute and solvent are. Let's see. Concentrated sulfuric acid we used to use in the lab was 98% by mass. It was very concentrated, and you want to be careful with it. Concentrated hydrochloric acid, though, was 37%. 30, I think it's 37% by mass. And even that, if you open the cap, it was fuming. So it gives us noxious hydrogen chloride fumes. And you'd want to work with that under the hood. Acetic acid, HC2H3O2. You can get that 100%. In fact, there's no solvent in that one. It's 100% acetic acid. They call it glacial. So if you ever see that term, glacial acetic, you know it's 100%. But it's still a liquid. All right. So these two examples, the one on the right is dilute, the one on the left is concentrated. And you can see the difference in the density of the color. Right, the concentrated one is a denser blue, a darker blue. One on the right is a lighter blue. And that's typical. When you have colored solutes, if you increase their concentration, you increase the intensity of that color. If we have aqueous solutions, we use that suffix in parentheses, AQ. That just means whatever the compound is over here is dissolved in water. Non-aqueous solutions, I'm sure there are some letters that you can put in there and identify it, but since we're not going to be using them, we're not going to do that. You just no aqueous and just no non-aqueous solutions exist. All right, so the temperature, as the temperature decreases, as increased temperature decreases gas solubility, increased pressure increases gas solubility. Okay, so we do have a theory about how solutions form. And this kind of helps understand the processes that are being modeled. We divide it into 3 steps. Now, like I've said before, nature just does what it does. And we're proposing these 3 steps just to kind of understand or rationalize what's happening. All these things happen at once. But this is the way we divide them. We have our solute here. We have our solvent here, whatever that may be. And then we have our solution where you put them together. Okay. The solute, in order to make it ready for making the solution, you have to break the bonds that are holding the various components together. Like sodium chloride, you need to break those ionic bonds. It takes energy. So we break bonds to get the separate components, and this is endothermic. That means it takes energy to do it. You have to put energy in. Okay. Similarly, for the solvent, we have to make room for those various components to go in. They often call it make a hole. And this is also endothermic. Because your solvent molecules have a certain attraction for one another, especially water. So you got to put energy in to get those things apart and make room for these components. And then when they come back together, you get solute, solvent interaction. And we're usually referring to attractive forces. And this is exothermic. So you get some or all of that energy back. Sometimes you get more energy back than you put in. So if we, let's see, no, it's not going to show it. All right, the symbols we use for this H stands for enthalpy or heat. So if we say this is that process, this is this process, and this one is that process, and that's a change of, just think of it as heat for now, the change of heat. So if we put energy in, this value is going to be positive by convention. If we put this energy in, it's going to be positive. We get this energy back, it's going to be a negative value. Everything is relative to the system. So if we put energy into the system, it's positive. If we take energy out, it's negative. But the total, this heat of solution, is equal to the summation of each one of these. Okay? So what we're saying is, since these are positive and this one is negative, if you get more energy back than you put in, then the summation is going to be negative. And that means exothermic. So the solution is going to get hotter. If this one, if you put more energy in than you get back, then the overall is going to be positive and the solution gets colder. And that's the idea behind making hot packs and cold packs in hospitals. You have these bags that have water in them, and they have a little breakable capsule inside that's got an ionic compound. And they have two different compounds. One of them, the hot pack, when you dissolve it, you favor that. You get energy back, it makes hot. And the other one makes it cold. Okay, so that's how we envision a solution being made. We break bonds, make a hole, and solute-solvent attractions. So that just talks about before and after, what we call equilibrium. In other words, we know how it started, we know how it's going to end, but we don't know how fast it's going to happen. That's in chemistry, that's called kinetics. But how can we make it happen faster? Right? If we want a solution to form faster, one way is subdivision, particle size. If you make the particle size of your solute smaller, then you have more surface area. The solvation process occurs at the surface of the particles. So if you have more particles for the same mass, you have more surface area. And the solution happens faster. Also, if you agitate it, you'll get the solution to form faster. What happens is when you have these particles, and I'm going to draw them real big. When you have these particles in your solvent and they're sitting there, just let them sit there, then you start to have these ions, right, go out into solution, but they tend to concentrate around the particle. And as they concentrate, then there are fewer solvent molecules there to do their business. But if you agitate them, then you're always introducing the particles as they shrink to fresh solvent. That makes the solution happen faster. And then there's the temperature. We know that solubility for most solids increases with temperature, or if you want more gas to be dissolved in your solution, decrease the temperature. That's why when I buy pop, say a 2-liter bottle, I don't open it right away, right? It's at room temperature. If I open it, what are you going to get? You're going to lose a lot of your fizz. So I stick it in the refrigerator for a couple of hours, cool it down so the gas is more soluble in the solution. Then when I open it, I just get a and I pour it in my glass and get a lot of fizz then. That's why I don't like going to picnics where they have the bottle sitting out on the table. Right. They're at what 80 or 90 degrees, depending on the time of summer. if you're going to do that, as soon as you open the bottle, you get the first, because before long, all the gas is gone and it's flat. So if you're the first one to the bottle, you'll get fizz before it has a chance to gas off, so to speak. Then there's the common ion effect. We haven't talked about that one. I sort of alluded to it here. If the solution already has some of the ions from your ionic solid, say we've got sodium chloride here in the solid form, but the solution already has sodium ions and chloride ions in solution, they will impede the dissolution of more solid, because there's just not enough. You're approaching solubility. So it's the solution formation slows down. There's competition for this space around these particles, and there's not as much solvent available. So the common ion effect will reduce solubility. All right. So since this is an introductory course, we're not going to go into as much detail or torture as I put my general chemistry class through. But there are some rules of thumb that help you deal with solutions. One of those has to do with polarity. And we talked about polarity, didn't we? Molecular polarity, yeah. If your solvent is polar and your solute is polar, you have a better chance of forming a solution. That's why we say like dissolves like. We're talking about polarity. Also, if they're nonpolar, both of them are nonpolar, those are more likely to form solutions. So if you try to mix oil in vinegar to make your salad dressing, you can't just put them together and expect them to form a solution for you. They won't do it. The oil separates and stays on top, right? Oil is nonpolar, water is polar. They don't mix. So if you want to form your salad dressing, put it in. I use those little chipped beef with the blue cap, little jars. Armor, I think, makes them. Once I get through making my SOS, I clean those up and keep them for my salad dressing. I put as much vinegar and oil in there as I want, and then I usually throw in some Mrs. Dash for flavor. And then you just shake it like crazy, hold it tight, and shake it like crazy to get the oil particles to be broken into very small pieces. You get a suspension. You don't get a solution. Then you pour it on your salad real quick before it separates. Now, there's a theory behind this, but I don't think we're going to go into that. It's beyond the scope of this course, I think. Yeah. We're just going to leave it at that. Let's see. Did I give you, I'm going to show it on the board in a minute. But let's see, where would it be? Here? Yeah, here it is. Okay. It's on the back of this review document. Solubility grid. Since you're not chemistry majors, then you're not going to be required to memorize rules of solubility. We're just going to use that grid, and that'll solve the problem. These are some of the rules, guidelines, you might say, for forming aqueous solutions of ionic compounds, right? Such as lithium, sodium, potassium, the alkali metal salts. So you form any anion with those metals that always go into solution. Or ammonia. If you have ammonium as the cation and then any anion, it will go into solution. Acetates go into solution. Nitrates, all nitrates are soluble. Like sodium nitrate, potassium nitrate, calcium nitrate, magnesium nitrate, they all go into solution. Now they have their solubility limits, but they do go into solution, and that's another topic that we can't get into, right? What's the actual solubility of some of these substances, other than what you can find in the reference manuals? Chlorides, all chlorides, bromides, and iodides are soluble except for those examples: silver, lead, mercury. They're insoluble. And we use these insoluble rules to help us separate metals, right? If we know that we have a mixture of various metal ions, cations, and we put chloride in there, we know we're going to get any silver, any lead, any mercury precipitated out, and we can separate them from the mixture. Sulfates. Sulfates are soluble except for calcium, strontium, barium, it's the alkaline earths, and silver and lead sulfates. Those are insoluble. All right, I'm going to skip the rest of them because those are the rules. Now, if you ever use these rules rather than the chart, the rules are set up so that if you have a tie between, say, rule 2 and rule 5, then the smaller number wins. All right, so there's your solubility chart, and that's what you'll have. You'll have this available on the exam. The cations across the top, anions down the left-hand side, and all you have to do is, I used to be able to tell my students to think in terms of a road map, where you have the mileage chart on the map. You've seen some old road maps. They will have a grid down in the bottom. They'll have, and you find your current location and your destination, and you just follow where they meet, and there's a mileage given for that. Well, similar to this, if you have your cation across the top, you say you've got a silver, and it's combined with chloride. Then you go down silver until you find the row where chloride is. You find it's grayed out. That's insoluble for our purposes. Okay, that's all you have to do. If it's clear, it's soluble. If it's gray, it's insoluble. And then there's some notes, but we're not going to deal with these. It'll either be soluble or insoluble for your purposes. The greater the difference between polarities of the solute and the solvent, the less soluble. Okay, now you can get some nonpolar and some polars together, and they're slightly soluble. But as a general rule, as they diverge, as their difference in nonpolar and polar becomes further apart, you get less solubility. So which of these ions are generally soluble in water that form a compound with lead? Well, notice E is another cation, right? It's not going to form a compound. Right, so that was a trick. Throw E out. So we look at sulfide, chloride, nitrate, and sulfate. If you look at that on the back side of your review document, and you follow lead down and say, okay, here's sulfide, here's chloride, here's nitrate, here's sulfate. Which one is clear? And you'll find nitrate is clear. Now, I already know that because I know that the rule says all nitrates are soluble, and those others, sulfide, chloride, sulfate, are not soluble. But your chart will tell you. Right? Nitrate is the soluble one for lead. Okay, how do we express this variable Well, I erased it. Variable composition. There are a number of ways to express that. And we're going to look at it, 2 or 3 of them. Let me check the schedule for a second. See, are we going to do, I'm interested in the labs we're going to do. Yes. Okay. In fact, our next lab, molar mass by freezing point depression. That's next Friday. We're going to use a concept in concentration expression, that bottom one, molality. And we'll get to it in a minute. Let's take them in order. Percent composition, molarity, and molality. Those are the 3 that we're interested in. There are other ways to express concentration, but the first one is any type of percent composition. And remember, percent is tricky because it is a dimensionless value. You have to know how the percent was calculated, because all it means is parts per 100 parts. That's percent. Now, are your parts here in mass units? Are they in volume units? Right? Are they in, say, grams? Are they in milliliters? Right? And the 100 parts, what are they in? Are they in mass also? Are they in milliliters? Right, so you can get mass per 100 milliliters, or you can get mass per 100 grams, or you can get milliliters per 100 milliliters. Right? Those are the most common ones. So you can have units of grams per 100 grams, and this is 100 grams of solution. Or you can have grams per 100 milliliters of solution. And by the way, if your solution is aqueous, if the solvent is water and the solution is dilute, then these 2 are equal, because 100 milliliters, because the density of water is 1 gram per milliliter. So they're the same. If you start getting concentrated solutions, then you're introducing the solute effect, right? And then it doesn't work. Percent by volume, right? All bottles of alcohol, wine, beer, all kinds of booze, they will be ABV, alcohol by volume. What that means is so many milliliters of ethanol, that's my abbreviation for ethanol, per 100 milliliters of solution. So that's volume per volume. Wines are like, well, let's see. Fruity pop wines are like 6 or 7% maybe. Most vintage wines are like 15 to 17%, something like that. Beers are now 6.4, I believe, 6.4%. Okay, so those are the, I mentioned that the Achilles heel of percent is knowing these values. Otherwise, if you're not given the percent, then you're in trouble, right? It could have multiple meanings. So this is how you calculate percent by mass. You just have the mass of the solute divided by the mass of the solution times 100. It's just that simple. Now, if you only have one solute and one solvent, then you just add those together, and that's the mass of your solution. The good thing about percent by mass is you don't have to worry. Mass doesn't change with concentration. right? Volume is variable with concentration, but mass does not change. So percent by mass is a good way to go no matter what the temperature is. It doesn't matter if the temperature is 0 degrees or 100 degrees, as long as they're still liquid or gas, then it doesn't matter. The mass by percent is still the same. Percent by mass. So what's the percent by mass of this one? We have glucose is 5.5 grams of glucose and 78.2 grams of water. Well, you have to add them together to find out the total. Oops, didn't show you, did it? All right, so we do 5.5 and 78.2. 5.5 grams plus 78.2 grams and 5.5 in the numerator times 100. And that should be equal to 6.6%. You know, if we follow our rules, we add these together, what do we get? 5.5, 83.7. Okay, we're still limited to two significant figures. Never mind. 6.6%. Percent by volume now is another thing. The volume of the solute going in, and then the volume of, well, this is relative. You know, that's another fly in the ointment. Is it the volume of the solvent or is it the volume of the solution? I think usually it's the volume of the solution. So if we have 30 milliliters of methyl alcohol, which is wood alcohol, that's the kind that'll make you go blind. So you don't drink that. And enough water to give you 435 milliliters of solution. Now we're talking, I think there's an error here. This is the volume of the solution. It should be whatever the volume of the solution is after you make the solution, because that's what this problem is using as its data. 30 milliliters of methyl alcohol in enough water to make 435 milliliters of solution. And that will give you 6.9%. All right, so that slide, I need to modify that slide. Let me make a note. Got that error. Here we go. This should be volume of solution. Okay. Mass per volume. This one gets it right. The mass by volume percent, mass of the solute per volume of the solution. Now, sometimes the solute will go into holes in such a way that the solution will have the same volume you started with. Sometimes it makes the solution get more, sometimes it makes it get less. So we need to know the volume of the solution after you make it in order to do this calculation. Now, like any value we get under this situation can be used as a conversion factor, as long as you know what the top and the bottom mean. Then you can convert one into another. So if you have, let's say, 15% ABV, right? Alcohol by volume, and we buy a bottle of wine that's let's see, I forget how much is in a bottle anymore. Is it a liter? Let's just, for argument's sake, let's say it's a liter. So a liter is 1,000 milliliters. So we have 1,000 milliliters of solution. We need a factor that will say milliliters of solution and milliliters of ethanol. It's 15 milliliters per 100. Right? Okay. So we divide this into that. It takes two of those and two of those. 10 times that is 150 milliliters of ethanol in that bottle. Okay. You can use these as conversion factors because they are equivalents. They're ratios. They're intensive properties. So if we have a mass percent of 10%, it contains what? Well, if we're just looking at the percent now, we're not trying to convert units. If it's mass percent, 10%, that's 10 grams of solute per 100 grams of solution. So how much of that is the solute? 10 grams. How much of it is the solvent? 90 grams. Okay. All right. How many grams of sodium chloride are needed to prepare 150 milliliters of 0.9% mass per volume sodium chloride? All right. Let's make some room here. Now, why did we choose 0.9% sodium chloride for this problem? Right, I got an idea. 0.9% sodium chloride is isotonic with your tissues. So if an EMT puts you on an IV, they're going to use either this concentration, probably not, but they could. If you need fluids, then they would use 0.9% sodium chloride in order to avoid destroying your red blood cells. Now, I could only envision sodium chloride being used like this if they knew you were diabetic. Then they wouldn't use one of the ringer solutions, like lactated ringers, because well, I don't know, lactated ringers might work. They wouldn't use anything with glucose in it, definitely. Okay, so if you have 150 mils of 0.9% mass per volume, okay, so we got 0.9 grams of sodium chloride per 100 grams of solution. That's what that means. If we have 150 milliliters of the solution, mass per volume, excuse me, milliliters. That'll work better. Then we can use this as our conversion factor. We have 150 milliliters of solution. That cancels. And we have 100, so it's 1.5 times 0.9. 5.9 is 13.5. Let's see if I did that right. Oops. Nope, I did something wrong. 1.5 times 0.9. Oh, duh. It's 135, but I've got a 0.9 times a 1.5, 2 decimal places. 1.35 grams. Now, the other problem with this solution is that, especially the chlorides, I can't remember which one's which is the worst one, but you're flooding your system with sodium and chloride ions. So that means your kidneys have to work overtime to stabilize your electrolytes. So you don't want to be on this for very long. Okay. Another way of expressing concentrations, which is extremely useful in chemistry, is molarity. The reason it's useful is once you've converted your solute into moles, then that concentration could be the same as some other substance, right? Once we got it to moles, it doesn't matter what the substance is, it's that concentration in terms of moles of solute. Now, it may take, depending on the molar mass of your solute, it may take more mass of one than another to give you that solution. But when we're doing stoichiometry, we're doing chemical reactions, we're interested in the number of particles, not the masses. So molarity comes in really handy. And all it means, this M stands for molarity, and it's the moles of solute per volume of solution. And the solution is in liters. That's molarity. Okay? And like any other equation, if you know the molarity and you know how much volume you have, then you can solve for the number of moles. Okay? So there it is, moles of solute per liter of solution. Now, there's just one problem with this. The molarity changes with temperature. Okay? Because of that. Right? Most liquids, all liquids, when you heat them up, they expand. So if it's at 1 molarity and you heat it up, the molarity value goes down because this gets bigger. The denominator gets bigger, the quotient gets smaller. So molarities are expressed in terms of temperatures. And the glassware that we use to be sure we have a certain volume of solution when we're mixing this up is calibrated at a certain temperature, usually at 20 degrees Celsius. Okay, we have 1 mole of sugar and 125 milliliters of solution, and we put those together. What's the concentration of the in units of molarity? Yeah, there it is. So notice with 125 milliliters, we have to convert it to liters. 125 milliliters is 0.125 liters. Is that reasonable? The units of measure got bigger, milliliters to liters, so the number has to get smaller by a factor of 1,000. Right, 1,000 milliliters in liters. That's why the decimal was moved 3 places to the left. So this particular solution is 8 molar. Let's see, another problem. If you have 10 molar sugar solution, what volume of the solution do you need to have 2 moles of sugar? That's where we're like this. And we want what volume? So now we're going to solve for volume. So I'm going to bring volume over here, molarity over there, like that. So we would just put in, we want 2 moles out of 10 molar. Okay. So what's that, 1/5 or 0.2 liters or 200 milliliters. I got this one animated. There you go. 0.2 liters. That's how much of that solution you need to guarantee that you possess now 2 moles of the solute. That's going to have something. Yep. Do this. Were you here last week?
No.
Okay. You'll need a copy of each one of those then.
Okay.
A sponge works better than my cloths. Okay, now we're getting trickier and trickier. Consider separate solutions of sodium hydroxide and potassium chloride. We're going to dissolve 100 grams of each. Yeah, 0 grams of each in 250 milliliters of solution. So the volume of both of them is 250 milliliters. That's the final volume. Okay, we know we're going to have to convert this to liters. So we move 3 to the left, 0.2500 liters. But we don't have moles up here. How do you get moles? Molar mass. It's just that simple. So what's the molar mass of sodium hydroxide? Well, we have to look it up. I can't see that far. Let me see. Where's my table? Or somebody tell me. What's the molar mass of sodium? It's like 23, I think. See if I'm right. 23 grams per mole. Oxygen 16, hydrogen's 1.01. 10, if I did that right. 40.01 grams per mole. Grams on the bottom, moles on the top, right? Because we got to cancel grams. Okay. And that'll tell us how many moles. Oh, I don't have my calculator out yet. Oh. Let's see, 140.01. I get 2.499. 499 moles. How about this one? Potassium. I guess I can go look. 39.10. And chloride is 35.45. 74.55. There we go. Divide that into 100. .341. 341 moles. Okay, so now all we have to do to calculate the molarity is moles per volume, 0.2500. This is moles per liter. So let's say 0.25. 9.9. Well, actually, we have 4 significant figures. Yeah, okay. 9.998 molar. And this one is 1.341. 0.25 liters. So let's pull that one up and divide by 0.25. This is 5.366 molar. Okay. So we had the same masses, but we had a different number of moles. Gives us a different molarity. All right, that was rounded off to 3. We didn't have to because we had 4 significant figures, but you get the idea. And then the other one is that. All right. Questions so far? Pretty straightforward. A long time ago, I don't know whether lab techs or nurses had to mix up solutions and put them in glass bottles and run them through the sterilizer, get them ready for patients. Now they come ready-made in plastic bags. So we eliminate that possibility of killing patients because you mixed up the solution wrong. But in my previous life, we used to analyze or extract soils for various nutrients. And we would use particular types of extractants, and they would be made up with several components. But we would do hundreds of them a day. So rather than mix up a fresh solution every morning, take you a couple of hours, we would mix up a concentrated solution with the correct ratio of each of the components. Then when we diluted it down to the correct concentrations for each of those components, we'd be ready to go, and that would take us like 10 minutes. So it saved a lot of time. Well, how does dilution work? Well, dilution in prose is a process where you take a concentrated solution of solute in solvent and add more solvent to reduce the concentration of all the solutes. Now, if we were going to do that, we would have this, we would have the concentrated, the molarity here of the concentrated solution. And then we would have a fixed volume over here that we knew, like we would use a volumetric flask. And these things have a line scratched on the neck. And that tells you exactly when you are at that point and the bottom of the meniscus is on that line, then you know you have a given volume in these. So let's make it simple. Say it's a 1 liter volumetric flask. So this is the second volume. The first volume is whatever you take out of this one. So we're going to take out of this one and put it in here. Volume 1. Or volume concentrated. Let's do it that way. Concentrated volume. This will be diluted volume. Okay? Now, what's the molarity of this one? Well, you can say what it is. That's what we used to do. We knew what this one was. We would say what this one was, what we wanted. And we would know this one, so we could calculate that one. Okay. So remember, the molarity equals moles per unit volume. So how many moles of solute are you transferring from here to here? Let's keep it simple. Let's say you only have one solute in this solution. The concentration, how many moles are you taking out? Well, molarity times volume. Concentrated equals the moles from the concentrated side. Okay. What's the concentration over here? Well, the diluted side has the moles of the solute and the volume. Thank you. So the number of moles going into that would be this. Right? Well, look, the moles that came out of here, did they change on the way? Oh, it's the same number of moles you took out went in here. So that means concentrated moles equals the diluted moles, exactly the same amount. Well, this one equals the molar diluted, the volume diluted, and this one equals the molar concentrated times the volume concentrated. Well, if A equals B and B equals C, then A equals C. that one equals this one. So that's why the dilution works. Because the moles taken out of here equals the moles going in there. Let's see, how would you prepare 100 milliliters of 0.9% saline in water from a 10% saline solution? Okay. So let's say we're going from the concentrated side at 10%. So the constant, and actually, the point we're making here is that it doesn't have to be molarity. Percent works also. But what we need to understand is what do we mean by percent? 0.9, originally we said we want this one to be 0.9% or grams sodium chloride per 100 milliliters of solution. And on this side, we have 10 grams of sodium chloride per 100 milliliters of solution. Okay. Well, this was explained for molarity, but it works for concentration too, because these are ratioed. So the values of concentration, they can be anything you want, as long as they're the same on both sides. So if we use their notation, we have concentration, the concentrated side, let's see, times the volume of the concentrated side equals diluted side. Okay, so the question is, well, how would you prepare? Okay. All right. Let's put in here what we know. The concentrated side is 10%, right? 10%. We don't know how much volume to take out. That's unknown. The diluted side is 0.9%. And the volume is 100 milliliters. Right? So if we solve for this one, it's going to come out in milliliters units. And let's see, this would be, let's put this one over here. There we go. So I should be able to do that in my head, but I don't trust myself. That would be 9 milliliters in 100 milliliters. So since it's a diluted solution, 9 milliliters, and we want to make 100 milliliters, would be plus 91 milliliters of water. That would give us 100 milliliters. So it should be that last one. Oh, it's going to work it out for me. There we go. Oh, that box. It doesn't have the font for that one. So it sticks a box in there between the 0.9 and the 100. That's a multiply. Okay. So we need 9 milliliters of the stock and plus 91 milliliters of water. It would be better if we actually put this into a 100 milliliter volumetric flask. Then we know we have 100 milliliters at the end. That would be the accurate way to do it. All right. So let's get rid of this and this. A 0.5 molar solution of sodium chloride sits on a lab bench. Oh, Which of the following would decrease the concentration of the salt solution? Sodium chloride is not volatile. So however much sodium chloride you have in that solution is the same at the end of the procedure. So we can either remove the solvent, or add solvent. That's the only possibilities. I mean, one of the options, it says pour some down the drain, right? That doesn't change the concentration. Add water to the solution, that would decrease the concentration. Yes, we're adding solvent. Pour some of it down the sink, no. Add more sodium chloride, that would increase its concentration. Let the solution sit out, that would also increase the concentration because we're removing solvent. And not at least two, just the one. Right? Add water to the solution. That would decrease the concentration of salt. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide? I didn't point this out before, but since these are ratioed to one another, you don't have to change that volume to liters if you use this formula. If you have a concentrated, well, in this case, we have 2 molar sodium hydroxide is the concentrated side. And we want to make 0.8 molar. We're looking for how much of that concentrated do we need to make 150 milliliters. Okay, so that's your equation. And the molarity is going to cancel and the volume units are going to be milliliters. Let's see, did I animate this one? Nope, I didn't. So what you have to do is solve for this one. And that's 0.8 times 150 divided by 2. And that should be equal to 60 milliliters. That's 60 milliliters of the concentrated solution diluted to 150 milliliters final to give you 0.8 molar. All right. We've talked about solutions up to this point, and the general topic for this chapter is solutions, but we have to include a discussion of something that looks like a solution, but it's not. And that's called a colloid. In fact, a colloidal dispersion is not a solution. It's based upon the fact that the dispersing medium that is analogous to the solvent has within it a dispersed medium, which is analogous to the solute. And the particle size on the dispersed medium is small enough so that the kinetic energy of the molecules in the dispersing medium can keep it suspended, right? But it's not a solution. And in fact, under certain conditions, it wouldn't be uniform throughout. Okay, dispersed phase versus dispersing medium are the terms that we use. And it's all dependent on the particle size. Now, how do we tell the difference? Well, there's something called the Tyndall effect. The Tyndall effect is, let's see, are we going to use that? Hold on a second. Let me check. I don't think we're going to have time to do it. I got a lab that uses that. No, sorry. The Tyndall effect is, say you have 2 beakers. Okay. And this one is a bona fide solution, and this one is the colloid. If you shine a bright light, lasers work better, but a flashlight will work okay. and you shine a light on this one right here, and you look at it from out here. You don't see anything at right angles to the solution. In other words, there are no particles in there that can disperse the light coming through and send it off in all directions. But when that light beam hits the colloid, some of those light beams hit those particles that are suspended. And now you can see them. That's the Tyndall effect. Oh, there we go. The one on the left is a solution. The one on the right is colloid, colloidal dispersion. And you can see the light beam in the colloidal dispersion. Okay. Now, just to contrast, suspensions are mixtures where the particle size, where the suspended medium does not dissolve in the suspending medium and will settle out over time. So when you mix them together, you're going to get a heterogeneous mixture. You're not going to be a uniform distribution of particles throughout. All we need is gravity or a simulation of gravity to remove those suspended particles. Some of them are so small that they will eventually settle out. But if you want it to happen faster, you stick them in a centrifuge and simulate gravity. Okay, this table came straight out of your book. It just draws distinctions among solution, colloidal dispersion, and suspension. All right, colloidal dispersion is all of those. Contains small particles that are not visible to the naked eye, but can be seen with the Tyndall effect. Mixture contains particles that don't settle out under the influence of gravity. Now, I suspect if you put a colloid in a centrifuge and spin it fast enough, you'll get those particles out. But it might take a really, really fast centrifuge. It's also, colloidal dispersion is also a mixture that contains particles that cannot be filtered out through large pore filter paper. So if you have small pore filter paper, sometimes you can get those particles out. But the smaller the pore, the longer it takes, or you need assistance, like vacuum filtration. Okay. So let's talk about colligative properties. Colligative properties are properties of solutions that, physical properties of solutions that depend only on the number of solute particles in the solution. So it doesn't matter what they are. For instance, we could have a 1 molar solution of sodium chloride, or a 1 molar solution of calcium chloride, or 1 molar solution of sodium nitrate, and they would all give the same physical response for a particular colligative property. It only depends on how much there is of each one. Actually, I should have been more specific. When I say 1 molar sodium chloride, what's the concentration of the ions in that solution? Right? Because they break apart. So that means now you have two for where you had one. I said 1 molar calcium chloride. That would be 3 molar ions. So that would be it would be a different response of the colligative property because it has more of the ions. And then what else? Sodium nitrate. Okay, that would be 2 molar. Because it breaks into sodium and nitrate ions. Okay, we use these colligative properties for various reasons, but one way we can use them is to help us determine the molar mass of an unknown compound. Right. Remember when we did empirical formulas? Does anybody remember that? Okay, and then we went from empirical formula to molecular formula, and we had to know the molar mass in order to make the transition from empirical to molecular. Colligative property is one way you can do that because it doesn't depend on what the substance is. It only tells you the number of moles in the solution. And if you know the mass that you put in the solution and use the colligative property to determine how many moles there are, then you can calculate molar mass, grams per mole, without even knowing what the substance is. Okay, the ones we're going to look at are vapor pressure depression or lowering vapor pressure, boiling point elevation, freezing point depression. That's the one we're going to do next week. Freezing point depression. Did I bring? Hold on a second. Be sure I got a copy of that one. Can I hand that? I don't. I have to print one. Don't think I brought it. Okay. I'll print that one while you're doing the lab. So you'll have it ahead of time. And then osmotic pressure. We use the colligative property of osmotic pressure to purify water in a process called reverse osmosis. Right. If you've had a biology course or an A&P course, you've probably been introduced to osmotic pressure. So you know solutions that are isotonic, those are hypertonic, and those are hypotonic, are related to osmotic pressure. And if you put red blood cells on a slide and drop distilled water on them, what's going to happen? Boom. They're going to suck that water up and explode. And it will happen in a split second. Or if you put a salt solution on those same red blood cells, what are they going to do? You know, crenulate. Right? Water is moving out of them. That's why we use the 0.9% sodium chloride solution, so that we wouldn't do that to our patients. Okay, so let's look at these vapor pressure lowering. This is based upon Raoult's law. Okay. And all it says is that the vapor pressure of a solution, the measured vapor pressure, is proportional if you know the vapor pressure of the solvent, right? The standard vapor pressure of the solvent, and then you know this factor of the solvent. So what does that mean? That means mole fraction. Just what it says, it's a fraction. In other words, if you take the moles of solvent and the total moles of the solution, divide the two, you get a value, a decimal fraction. It's always less than 1. If it's equal to 1, what do you got? You got a pure solvent, right? So something less than 1 here. And the vapor pressure, we know what this vapor pressure is for the pure solvent at a given temperature. And then if we know the mole fraction of the solvent in the solution, we can calculate the vapor pressure. So let's say we have a mole fraction of sodium chloride in solution of the mole fraction of sodium chloride is 0.2. What would the mole fraction, assuming there are only 2 components, the mole fraction of the solvent would be 0.8, right? Because they have to add up to 1. And then we put 0.8 here, and then we need a value for this pure solvent vapor pressure at that temperature. Then we can calculate it. That's Rayleigh's law. And it actually lowers the vapor pressure by putting a non-volatile solvent, solute in our solution. We lower the vapor pressure. Here's an illustration, and we're trying to rationalize, I should say, the lowering of vapor pressure. Vapor pressure is produced by the evaporation of the solvent molecules into the vapor phase, and we can only measure that pressure if the container is stoppered. It builds up an equilibrium. We talked about that before. If you have, say, a flask, and you stopper it, and you have a pure solvent down here, then when you first stopper it, evaporation is one direction. You're going to get some of these molecules moving into the vapor phase at a given temperature. Once you reach a certain concentration of these molecules up here, they're going to start returning. And we set up an equilibrium to where the physical equilibrium, where the condensation equals the rate of evaporation. And at that point, you can measure a pressure. That's the vapor pressure. Now, if we put a non-volatile solute in there, it does 2 things. It takes up space at the surface, so we don't get as many molecules moving into the vapor phase. The other thing it can do is because these solute molecules went into solution, then we know that there's some attraction between the solute and the solvent based upon that 3-step process we saw earlier, that they're going to impede the movement of the solvent molecules into the vapor phase. So both of those effects, physical interference and attraction, will reduce the number of molecules of the solvent going into the vapor phase, which will decrease the pressure. That's the explanation for Rayleigh's law. All right. Next is boiling point elevation. Boiling point elevation. So we have a boiling point for our solvent. And if we add a solute to it, it will cause the boiling point to increase. And the law that governs that is the change in temperature between the pure boiling point and the solution boiling point, that change. And actually, we're only interested in the absolute value. If you come out with the negatives, just throw the negative out. Is equal to some constant times the molality of the solute. Okay, we didn't discuss molality, did we? Just molarity. Molality is like molarity. Right? Molarity is moles per volume. Molality equals moles per mass. This is in liters. This is in kilograms. Let's see. Yeah, kilograms. The reason we want to use this one is because we're changing the temperature. And remember what happens to molarity when you change the temperature? It changes. We don't want the concentration to change based upon our measurement. So we use this version because it will not change with temperature. Okay. So molality then would be units of measure would be moles per kilogram, right? Okay. And this temperature is degrees C. This is one where you don't have to change it to Kelvin. It's degrees C. So that means this one, in order to give you degrees C, would have to be degrees C on top, kilograms on top, and moles on the bottom. So degrees C, kilogram per mole. Or sometimes you'll see it degrees C divided by molality. Because molality is moles per kilogram, but if we put kilograms on top, moles on the bottom, we're actually dividing by molality. Okay? So that means, yeah, kilograms cancel, moles cancel, leaves us with that. So that's the constant is going to have units of degrees C, kilograms per mole, or degrees C per molal. And you have to be given that value for the solvent. Right? It's a different value for each solvent. 0.51 degrees C per molal is for water, boiling point elevation. Now, where do we make use of that factor? Antifreeze. If you just put water in your radiator, as soon as it gets hot enough, the valve is gonna pop and you're gonna start losing steam. So we put antifreeze in it. We increase the concentration, the molal concentration of the ethylene glycol, and that increases the boiling point. So you can run your engine hotter than 100 degrees. I see. What are most thermostats? 150, 60 C? I don't know. It depends on the engine. Some of them run hotter than others. It's probably pretty high for small engines. We're working them harder. They're hotter. That's why they're more efficient. But that's another topic. That's thermodynamics. Freezing point depression, right, is similar to boiling point elevation. This is the one we're going to use for next week, depression. So here again, we get this absolute value, temperature change. The temperature change is between pure solvent and solution. So for us, we're going to measure the freezing point of pure solvent, and then we're going to put a solute in it of a known amount and measure the new freezing point, which should be lower, and then subtract and get a delta T. Then we have another K value, this time for freezing point, times the molality of the solute. Okay? Similar units of measure, but that will be a different value depending on what your solvent is. We're going to use it to find out this right here, moles per kilogram. And Actually, we're going to use this value to calculate the molar mass of, let's see, I think it's benzoic acid. We're going to use lauric acid as our solvent, benzoic acid as the solute, and determine the molar mass of benzoic acid. We know how much the mass of benzoic acid that we put into it to get that difference in temperature. And then if we know this one and the mass of the solvent, then we can find out how many moles. Now we got mass in moles, we can calculate the molar mass of benzoic acid. All right. Let's see. How does the addition of non-volatile solutes to a solvent affect the vapor pressure? It decreases it. Osmosis. All right. Let's see. Let's make room over here. Get rid of Raoult. Osmotic pressure. Okay. Osmosis is describes the passage of a solvent through a membrane between two different solutions. And what we're saying is that for a semi-permeable membrane, for a semi-permeable membrane, only water may pass. Not even the Balrog can get through this membrane. Okay, it says semi-permeable, only certain types of molecules. We're going to restrict our semi-permeable to water as the solvent. That can go through and nothing else can go through the membrane. So, well, small gas molecules can, but they're generally not part of the solution. So we don't worry about them, except under special conditions, and I'm not going to bore you with those. So when we have this membrane here, and say we have pure water on this side. Now on this side we have aqueous sodium chloride. Okay, let's just make it easy. Say it's 0.5 molar. If only water can pass, which way is the water going to move? It's higher concentration here. These water molecules are striking the membrane from this side. Water molecules are striking the membrane from that side, but they're more frequent from this side than they are from that side. So water is overall going to pass to the right. Okay. Now, if we put, let's say, let's do this. That. And say we have a membrane here. Now we have our water on this side, and we have our sodium chloride on this side, aqueous. Okay? And we have, say, this much water on that side and equal amount on this side of that solution. Then they will eventually reach equilibrium when the rate of movement of water this way equals the rate that way. But in order to get the rate to be equal coming this way, we need to add some extra pressure, some force behind it to make it move that way. So that happens when this water level drops down to here, and this water in this solution level goes up to here. Now between here and here is our osmotic pressure. Okay. We've added enough pressure on this side now that the water movement in both directions is equal. That's what we mean by osmotic pressure. Now, the other type of membrane, and I think we're actually going to get to do an experiment with this. I believe it's maybe the last one. No, next to the last one. Osmosis and dialysis on November 15th. We'll use actually plant cells to mimic the semi-permeable membrane. And then I have some special tubing that will allow us to mimic the selectively permeable. In this case, selectively permeable is size limited. The pore size on the membrane is arranged so that only molecules of a certain size will pass through. So we're going to use something like glucose compared to starch. Glucose is a real tiny molecule. Starch is a huge molecule. That's the difference between those two. All right. So here's another way of representing osmotic pressure. The more concentrated solution is inside the tube, so the water is going to move in through the membrane until there's enough head pressure to equal the force on the molecules, water molecules going in both directions. And it's measurable. And frequency of impact is the key. Now, if we want to reverse, if we want to move water this way, say we have seawater or brine of some kind on this side, we want to remove the salt so that we can drink it. All right, so places like Saudi Arabia, they don't have much natural water sources, or some places in California, I think, are using reverse osmosis. You artificially increase the pressure on the brine side, and it starts driving water this way, and you take that off to your product stock, your product output, and the brine stock becomes more concentrated, and you bleed that off in a continuous fashion, and dump it back in the ocean, where the little that you put in won't make a big difference. It's diluted out. That's reverse osmosis. We used to use that procedure to pre-treat the water for our lab where I was working for the USDA. And we would have a reverse osmosis system in another room because it get kind of noisy when the pumps turn on. And that feed water would go through plastic pipes to each of the labs. And then at each of the labs, that water would be fed into an deionizer, which would further purify it. And it depends on what you were doing in your lab as to what type of water polisher that you would use. Okay, how are we doing? We need to start our labs at 11:05. Let me see. Is this the last slide? Am I getting close? Not quite. I'll have to make this one quick. You can see there's a picture of the sequoias in California. And for scale, we've got a man standing over there on the left. These trees are huge. It always puzzled me. How did water get from the ground where it had to come from for the tree to the topmost branches? How did it get up there? For a long time, the theory was that as water evaporated, surface tension pulled it up. And if you have a leaf and you have these stomates open to the atmosphere, and the guard cells would open up and let the water evaporate. Then if you have water here like this, and then some of it evaporates, now it's like this, but it's trying to pull itself back, surface tension. And that would produce a lifting force. And you'd have billions and billions of these little areas that would be pulling. So I figured, well, maybe that's enough to pull water up. But some bright scientist, probably a graduate student, did some research and found that it wouldn't work. It's not enough. Even if it did work, it wasn't enough to bring water to the top. So we had to go back to the drawing board. So if it's not a pull, then maybe it's a push. So some scientists measured the osmotic pressure of the solution outside the root cells, right? And say, okay, inside the root cells and outside versus one or the other, and measured what is the difference in pressure between the cells, the internal concentration of solutes in a cell versus outside the cell. And it turns out that in the roots, the osmotic pressure exceeded 20 atmospheres. That's massive pressure. So those cells have to be pretty strong to build up that much pressure. Okay, the question now is that enough pressure to reach the top of a tree? Right? Some of these trees are 300 feet tall. So with that pressure, what I wanted to do is find out, all right, how tall is this tree in millimeters? And here's the reason I'm doing that. 300 feet is 9.144 times 10 to the fourth millimeters tall. All right. How tall would 20 atmospheres be for a column of water? Right. 20 atmospheres would give you a column of water, and I just converted atmospheres to millimeters of mercury because I know that conversion factor. And then the difference in density between mercury and water is 13.56. That would give me, first I'd have the column of mercury, then I'd change it to a column of water with that density difference. And I get, with 20 atmospheres, that water could go as high as 2 times 10 to the fifth millimeters tall. So that's a little over twice as high. So we could theoretically have a 600-foot tall tree, and it would still reach the top under these conditions. All right. There's another unit of measure that we use sometimes called osmolarity. Now, theoretically, if you know the molarity of a solution that's, say, inside the cell, and you're trying to determine what's the osmotic pressure for, say, the pure solvent moving into the cell, like we did for the sequoias, then you would take molarity, the molarity of the solutes inside the cell, and multiply them times a factor. It's called the Van Hoff factor. Now, for general purposes, I means the number of particles that are produced for each dissociation of a molecule. So I for sodium chloride would be 2. So we just take the molarity and multiply by 2. So if it's a 1 molar solution, we'd have an osmole of 2 molar. Now that's generally speaking. There are other factors that affect, especially as the concentrations increase, there are other factors that affect this I value. One of the most prominent one is ion pairing. So if the concentration of sodium and chlorine gets too concentrated in the solution, you'll start to get pairs. And that'll reduce that I from 2 down to maybe 1.9 or 1.8. But that only happens in really concentrated solutions. And that would probably be the case in those sequoia cells, root cells. Because they'd have to be really concentrated to produce 20 atmospheres of pressure. So I for sodium chloride is 2. And if it was 3 molar, it'd be 6 osmol. Okay, hypotonic solution is one that has a lower osmotic pressure than within the cell. So that means water is going to move into the cell, because if it's a lower osmotic pressure outside the cell, that means it has more solvent than inside the cell. So that means the solvent's going to move into the cell through the membrane. Yes, indeed. Hypertonic means the solution is a higher osmotic pressure than within the cell, which means the solvent concentration outside the cell is lower than inside the cell. Water would move out of the cell. And of course, isotonic means they're balanced, perfectly balanced. All right. That's what they would look like. Oh, I did the calculation. I forgot I did that. So the one on the left is just before it explodes. The one on the middle is the crenellated cell, which is a result of a hypertonic solution in its environment. And then the way the cell's supposed to look on the right. It's like a donut without the hole. Now this, an isotonic solution, if you can give your patient a glucose-related solution, they call it D5W, dextrose 5% by weight. Actually, it's weight volume. So every EMT knows what D5W means. The osmolarity of that solution is 0.2775, which is neither here nor there unless you're actually in the business. But if we compare that to 0.9% sodium chloride solution, it has a slightly higher osmolarity. It also introduces, oh, here it is. Okay, I knew I had it somewhere. The sodium you introduce with that solution, the 0.9% sodium chloride, you introduce 10% more sodium than your body needs. That's not a big insult, but you introduce 50% more chloride than the body needs. So what your kidneys are going to have to do to get rid of that chloride is sacrifice other cations. Right? So what it will probably do is they get rid of that chloride is they're going to strip out sodium, potassium, calcium, those cations, and you're going to become deficient in those over time. So you're going to have to replace those. And if you want more information, I've got the link down here that describes that whole calculation. All right, there's an isotonic solution. How is the osmolarity of a solution determined? We just multiply the molarity times the number of particles produced per formula unit. And that's where we're going to leave it. We're not going to go into those anomalies. So we've got a couple of concept questions. That means we're right at the very end of this chapter. And I'm just about out of time. We might have to forego these because I don't want to eat up any of your lab time. Let's see. How would you prepare 200 milliliters of 0.8 molar sodium hydroxide, molar mass of 40 grams? Okay. I think you can do that. Oh, I have it animated. Okay. There you go. Find out how many moles you need. All right. So that's 0.16 moles of sodium hydroxide. And then convert that back to grams. So we're going in reverse from what our earlier problem was. This is how you would determine, okay, I need a 0.8 molar solution of sodium hydroxide. And I'm going to make 200 milliliters of it. So we find out how many moles of sodium hydroxide you need, then change that to grams. That's how much you measure out and dissolve to a volume of 200 milliliters. There it is. Let's see, what's this one? If you add 2.6 grams of sodium chloride to 300 milliliters of water, what's the molarity percent? Mass, volume, and osmolarity. All right. I'll let you work that one out. You just have to do three different calculations. 0.15 molar, 0.9% mass volume, and 0.3 osmolol.